Assalamualaikum to everyone. A very good day. Okay, so for today we continue with the topic on fundamentals of thermodynamics, focusing on first law of thermodynamics. So today we discuss about energy in steady flow. This is the part 3 for first law on thermodynamics. So in part 3 we have two parts, part 3a and part 3b. Part 3b we will discuss after this slide, after these topics. Okay, so for today we focus on part 3a, energy in steady flow. Okay, as per introduction, what is energy balance for steady flow system? Steady flow process is a process during which a fluid flow through a controlled volume and it steady. We assume it's a steady flow. The fluid properties can change from point within the control volume, but at any point they remain constant during the entire process. Thus, volume, mass, m, boundary work, and total energy remain constant. So, for example, if we have a mass balance for steady flow system for a single steam, which means that we have a single inlet, we have a single outlet. Okay, so your mass inlet M1 is equivalent to mass outlet M2. So for mass is a rho times velocity times area is equivalent to your rho outlet, velocity outlet, and also area for outlet, whereby your rho is your density and vel is the average velocity. Because we need to differentiate, if we use a V, we may confuse with volume, but here for velocity we use vel. So this subscript we use for velocity. So for multiple inlet and outlet, so your summation of inlet is equal to summation your outlet. So which means that something like this, we have a 2 inlet M1 and M.2, 2 inlet. So your outlet will be M3, whereby your M3 is equals to M1 plus M2, something like this. Alright, so during a steady flow process, the total energy of control volume remain constant because we assume at a steady flow, and thus the change in total energy of the control volume is 0. Therefore, the amount of energy entering a control volume in all form, either heat, work, or mass, must be equal to the amount of energy leaving it. Total energy in is equal to total energy out. So the general energy balance equation can be written as, so energy in minus energy out is equal to change in a system for divided by time. So as we assume the equation is in steady state, so this is a transient. So for steady state, this equation will assume to be 0. Thus we have total energy in is equal to total energy out. So energy transferred by mass. In general, approximation of steady flow process can be illustrated in figure aside, this figure. So assume this is a piston, so we have a force acting upon the piston. So the area of your piston, so the force acting will be your volume, your pressure, and your mass. This is your total length. Okay, so the work energy is required to push the mesh into or out of the control volume. So we require control volume. This is your control volume. So if you require a total work here can be calculated in order to know how much for your outlet work. So this work is necessary to maintaining a continuous flow through a control volume. So from this equation, from this example, knowing that your force is pressure times area, then the workflow is force times length is equals to pressure times area times your length, and you got your pressure times volume in a unit or kilojoule, or workflow specific volume we have kilojoule per kg. So the specific energy of a flowing fluid can be written as total energy is equals to internal energy plus kinetic energy plus potential energy, which is your internal energy plus Val to the power of 2 divided by 2 plus Gz, gravity times height. Thus, the specific energy transport by mass of the flowing fluid, theta, specific energy, is the summation of the work required to push the mass, workflow, and the specific energy of the flowing fluid energy can be written as theta, your pressure times your volume, plus energy is equal to PV plus total internal energy, kinetic energy, and also potential energy. So knowing that your enthalpy is U plus PV for a fluid, a general equation. So we have theta is enthalpy plus kinetic energy plus potential energy is equal to H plus enthalpy, H Val to the power of 2 divided by 2 plus Gz. So in general, based on the previous equation, we understand that the energy transport by mass is taken care by the enthalpy. So in fact, this is the main reason for defining the properties of enthalpy. Hence, the equation can be written as, so total heat in plus work in is a summation of mass equal to energy out, heat out, or losses out, heat losses, or work produced out, plus summation of mass. So by adding all elements, heat, work, and mass flow, the energy balance equation for steady flow becomes, so your theta, substitute theta here, we got the theta here. So this is the inlet, this is for outlet. So student need to differentiate which is the outlet, what is the outlet, either the heat being introduced to the system, or is a losses we assume as a out of system, or work being produced, or work needed we assume as a work in, work produced we assume as a work out. So some steady flow engineering device. Many engineering devices operate essentially under the same condition for a long period of time. The component of a steam power plant, either turbine, compressor, heat exchangers, and pump, for example, operate non-stop for months before the system is shut down for maintenance. Therefore, this device can be conveniently analyzed as steady flow device. So, in this topic, MAC 451 cover the primary steady flow engineering device as follow: nozzle, diffuser, turbine, compressor, pump, throttle valve, mixing chamber, heat exchanger and condenser, also combustion chamber and boiler. So we proceed into the first machine. We call it as a nozzle and diffuser. So nozzle and diffuser are commonly utilized in jet engine, rocket, spacecraft, and even garden hoses. So a nozzle is a device that increases the velocity of a fluid by reducing the pressure. Diffuser, in other cases, is a device that increases the pressure of a fluid by slowing it down. So this is your nozzle. Your velocity, outlet velocity, is much more higher from your inlet. This is a diffuser. Your inlet velocity is higher compared to your outlet velocity. So the cross-sectional area of a nozzle decrease in the flow direction for subsonic flow and increase for supersonic flow. The reverse is true for diffuser. Diffuser and nozzle are shaped so that they cause large change in fluid velocity and thus kinetic energy. General assumption for nozzle and diffuser, there is no heat being transferred. So your Q will be 0. And also no work in and work produced for nozzle and diffuser. So we assume your work is 0. And normally potential energy, change in potential energy, is also assumed as 0. So thus the energy balance for nozzle and diffuser become, so we take out your Q, we take out your work, we take out Q, work, and also no potential energy, take out. So we have only mass we can cancel out, same mass, M1 is equal to M2, take out, is only this portion, enthalpy and kinetic energy, enthalpy and kinetic energy, inlet and outlet. So very be careful with the unit conversion. Sample problem 3.14. Sample problem 3.14. 3.14. Steam at 0.4 megapascal, 300 degrees Celsius, enter an adiabatic nozzle with a low velocity and leave at 0.2 megapascal with a quality of 90%. Find the exit velocity. Alright, so here given problem 3.14, we are dealing with steam. So steam, here we can acknowledge that we will refer to steam table. Alright, okay, and also given at P1 is 0.4 MPa and T1 is 300 degrees Celsius. So we are dealing with a nozzle, something like this. So inlet, outlet. So P1, T1, P2, T2. Alright, okay, and also the nozzle is adiabatic. Okay, and P2 0.2 MPa and quality 90%. Okay, so this is the general information given. Alright, so as we are dealing with nozzle and something like this, we must write the general equation first. So general equation, Q in plus work in plus summation of mass, enthalpy plus velocity 2 plus potential energy equivalent to Q out plus work out plus summation of mass and enthalpy plus velocity plus potential energy. Okay, alright. So from this general equation, we need to take out what is the unnecessary item that not involved in the problem. So basically here, the nozzle is not producing or required any work. So we take out your work nozzle, and also it's adiabatic. Okay, so adiabatic mean no heat in or injected or heat being rejected. Alright, and also the mass, so we can take out also same mass. Right, okay, and here also we assuming that is no potential potential energy. So left is only H1 plus val 1 is equivalent to H2 plus val 2. Alright, and the keyword here also mentioned in the question is low velocity at the inlet. So it means that your val is 0, nearly to 0, because it's a low velocity. We'll assume it's a 0 condition. So we take out, so rearrange the equation. So H1 minus H2 is equivalent to val 2 over 2. Alright, okay, so from here we need to find what is the question is find the exit velocity. So we need to determine what is your velocity val 2. So at state 1, so we are dealing with steam. So P1 0.4 MPa and T1 is 300 degrees Celsius. From these 2 points, 1 and 2, so we can locate where is the exact location in the steam table. So either is in the mixture, compressed liquid, or in the superheated region. So by determine the temperature, so refer T sat, what is your value? So from here, 300 degrees Celsius is exceeding the T sat. So which means that it in the location of this point is in the superheated region. Okay, so from superheated region we can determine the at 300 degrees C. So we found out that your H1 is a direct value. Okay, alright, and then we move on into the H2. So state 2. So state 2, given P2 is 0.2 MPa and the fraction given is 0.9 or 90%. So which means that the fraction between the quality of the steam, so means in this condition, so it's in the mixture because we have a fraction mixture. So in the mixture condition, so we can find out that so H2 minus HF per HFG is equal to your X or percentage or 0.9. So H2 kilojoule per kg. Okay, so substitute into the general equation. So we have general equation H1 minus H2 is equal to val. Okay, so here we have meter per second power, and also here we have kilojoule per kg or joule per kg. Okay, all right. So from we have value, so val is set 2 H1 minus H2, so we can have the meter per second. Okay, so unit conversion, joule per kg is equal to Newton meter per kg. So rearrange, we have K Newton. Newton is a force, so we have kg per second square times meter per kg. Okay, kg meter, sorry. Okay, substitute, so we have meter per second square. So same. All right, thank you. Sample problem 3.15. Sample problem 3.15. Air at 10 degrees Celsius and 80 kPa enter the diffuser of a jet engine steadily with a velocity of 200 meter per second. The inlet area of the diffuser is 0.4 meter square. The air leaves the diffuser with a velocity that is very small compared to the inlet velocity. So the question is, determine the mass flow rate of the air and B, the temperature of air leaving the diffuser. Alright, so here 315. We have a diffuser. Inlet, outlet. Okay, so the inlet, we are dealing with air. Okay, so basically here P1 given 80 kPa. T1 P, T1 is 10 degrees C. Okay, and V1 given directly 200 meter per second. Area, inlet area, area 1 is 0.4 meters square. So here we don't know the it's not given any pressure or temperature at outlet. So basically the information given is only at the V is very small, so which means that V2 0. Okay, so write your general equation. So Q in plus work in plus summation of mass H enthalpy velocity V1 squared over 2. This is velocity, not volume, plus potential energy ZZ is equal to Q out work out plus summation plus summation of mass enthalpy 2 means this enthalpy 1 enthalpy 2 plus V2 over 2 squared plus GZ. Okay, so we take out the unnecessary item inside here. So basically we assume it's a adiabatic condition. Okay, so adiabatic means no heat in an outlet. So the diffuser not producing any work and required any work. So we don't have also the potential energy, and the mass can be cancelled out. So leaving H1 plus V1 squared over 2 is equivalent to H2 plus V2 squared over 2. Okay, and also your V2 is small, 0. So we have V1 squared over 2 is H2 minus H1. Okay, so this is the general equation. Okay, the first question is to determine the mass flow rate. Mass flow rate M dot. M dot is rho AV. Is equivalent to rho kg per meter cube. Okay, so which means that times area m square times velocity meter per second. Okay, so meter cube per kg is specific volume, so it's 1 over v squared, something like that. So we are dealing with air. Not to forget, we are dealing with air. So from ideal gas, PV MRT. Okay, so this is the general equation for air. So P1, this is a volume, this is valve, this is volume, T1. Alright, so universal gas constant for air, RA, you can check at the tables, A2 tables for air. Okay, so T1 is given directly. Mass we don't have, so the volume also we don't have, so we take out. It's not take out, means PV specific volume RT1. So we have in terms of specific volume. We can relate it to this. So P1 specific volume 1 RT1. So specific volume 1 is RT1 over P1. So we have all the value. So we have meter cube per kg. Okay, and then substitute this function into general equation m dot. So sorry m, okay, m dot rho a v, so is equal to 1 over 1 a v. So this is your inlet velocity, val 1 1. So area has been given in the question. Velocity, inlet velocity also given 200. Val 1 is 200 meter per second. So we can get the mass flow rate, kg per second. Okay. The temperature B, temperature T2, air leaving the diffuser T2. Okay, so here the relationship between these two is H2 is Cp T2. This is from ideal gas. Okay, so Cp is a constant, so you can Cp, you can find it on Cp at table A2, something like A2 or A1 table in the appendix. So we can determine the enthalpy too, but currently we don't know what is the enthalpy too. So firstly we need to calculate what is your H2 enthalpy too. So from the general equation we have from last, so H2 minus H1 is equal to val general equation val 1 H2 H1. Okay, so val 1 over 2 square. Okay, alright, so we have that H2 minus H1 val 2. Okay, so H1 we need to calculate first. So H1 is CpT1, same, but it's a T1. So we have directly Cp from the tables appendix, and T1 is given directly at 10 degrees C. So how much value times 10 degrees C plus 273. So you got your kilojoule per kg. Okay, so we have val 1 val 1 we have also, so H2 is equal to kilojoule per kg. So val 1 is 200 meter per second, H1 H2 directly. Okay, thank you. Turbine and compression. Turbine and compressor. Turbine, a machine in which the kinetic energy of a moving fluid is converted into a mechanical energy by causing a blade rotor to rotate. The moving fluid may be water, we call it as a water turbine, steam, we call it as a steam turbine, or air, also we call it as a wind turbine, or combustion product of a jet, of a fuel, we call it as a jet. And it's a compressible and incompressible fluid. As the fluid passes through the turbine, work is done against the blade, which are attached to the shaft. As a result, the shaft rotates and the turbine produces work. Compressor, a device used to increase the pressure of a compressible fluid. Work is supplied to this device from an external source through a rotating shaft, normally a motor. A motor will produce work for a compressor. Compressor is very similar to pump and fan. Normally, compressor is used for air. To transfer air from one side to another side, we use a compressor. For fluid, normally, for liquid, normally we use a pump. We don't use a compressor for a liquid. So, general assumption for Q is equal to 0. We call it as a well insulated. And also potential and kinetic energy also we assume negligible. Okay, so basically this is your compressor, this is your outlet, this is your inlet, and this is a steam turbine inlet, this is your outlet, and it produces work. For compressor, we required work to move the shaft. For energy balance for turbine and compressor, so as we assume is no heat produced inlet and outlet, so we can take out your heat in and out unless it stated by the problem or exercise that your compressor or turbine producing heat. If not, normally in general we assume that the turbine and compressor will not associate with heat. So normally heat is taken out either in and out. So for turbine, normally we have work out, it producing work, so work out is there, and kinetic and potential energy has been taken out, so we have enthalpy with math, and also work out, mass out. So as mass, we have one inlet and outlet, so the total mass in and mass out is normally similar, so we rearrange, so we have something like this. So work out producing by the turbine. So this is for compressor. So compressor require work in. So from general equation, work in is there, but we cancel out the work out. So work in plus your mass and enthalpy out. So mass in and mass out normally is similar because we have one inlet and one outlet. So we rearrange the equation. We have work in is equal to mass flow rate times your change in enthalpy. Sample problem 3.16. Sample problem 3.16. The power output of an adiabatic steam turbine is 5 megawatt. Inlet, given directly the pressure 2 MPa, temperature 400 degrees Celsius, velocity 50 meter per second, and Z, the potential energy, is 10 meters, while the exit is pressure 15 kPa, X fraction is 90%, velocity is 180 meter per second, and the Z, the height 6 meter. The question is compare the magnitude of change in enthalpy, change in kinetic energy, and change in potential energy, and determine the work done per unit mass of the steam flowing through the turbine and calculate the mass flow rate of the steam. So firstly, compare the magnitude. So 3.16 is a turbine. So turbine, draw a turbine. Okay, so this is your inlet 1.1, this is your outlet 0.2. So at 0.1 given P1 2 MPa, T1 400 degrees Celsius, V1 is velocity, L1 is 50 meter per second, and Z1 is 10 meter, while the exit P2 is 15 kPa, kilopascal, and the fraction X, fraction 90%, so which means that is in the mixture condition. The velocity Val2 also given 180 meter per second, and also the Z is 6 meter. Alright, so general equation. Okay, firstly is compare the magnitude. A, magnitude of delta H, delta KE, and also delta potential energy. Okay, so delta H, H2 minus H1. Okay, and delta kinetic energy is V2 minus V1 over 2000 cos. Okay, this is a general equation. Okay, and also potential energy, G Z2 minus Z1 per 1000. This is your general equation. Alright, so maybe you are wondering, asking why we have 2000 here. Normally we have 2. Okay, so you can check back slide the unit conversion. Where is your val is meter square per second square is equal to joule per kg. Okay, so basically if you have a kilojoule per kg, so you need to move out. Okay, sorry, it's a joule per kg. So if you want a unit in kilojoule per kg, so you need to times kilo. Okay, so kilojoule 1000 Okay, so here is a joule times your joule, kilojoule per kg. Okay, so substitute into your here. So V2, general equation is a V2 times 1000. So here we got, you need another 1000, so you have from to have a kilojoule per kg, so you need a 1000 kg. So we have a kilojoule kg 1/1000 kilojoule per kg. Well, okay, so substitute. If you have a val, if val squared over 2, so it's a 1/1000 val squared over 2. So times, you got val 2000. Okay, all right, so that is the unit. So please be careful with your units, huh? Okay, so the task is come back to the original enthalpy H2, sorry, delta H is H2 minus H1. So at state 1, given state 1, given P1 is 2 MPa and also T1 is 400 degrees C. So as we are dealing with steam, so we refer to steam turbine, steam tables. Okay, so we have 2 points, 1, 2. Okay, check your Tsat. If T1 exceeding Tsat, so it's in the superheated region. So as Tsat is much more smaller to T1, so it's in a superheated. So get your H1. Okay, state 2, P2 15 kPa, X2 is given directly 0.9, so it's in the mixture because given the fraction, the quality of the steam. Okay, so from here you can have H2 minus pendek perpanjang, okay, HF2, alright, per HFG is your X, 0.9. So H2 kilojoule per kg, kilojoule per kg. Okay, so substitute into your enthalpy. We got kilojoule per kg. Okay, alright, so second is to determine the kinetic energy. Kinetic energy is V2 minus V1 square over 2000. Okay, so V1 and V2 is directly given, so you can solve directly lah. Okay, so the units is also kilojoule per kg, same units. Okay, potential energy G Z1 minus Z over 1000. Alright, so basically here Gz also same with velocity, so you need to have a kilojoule per kg So Gz is only joule per kg, so you need units of kilojoule. So unit here is if you don't divide it by 1000, so you have a joule per kg. So in order to get kilojoule per kg, so you need to add 1000 units conversion. So you can see the unit conversion for this. Okay, so the gravity is 9.18. Z2 and Z1 is also given directly, so you can get the answer kilojoule per kg. Okay, alright, so in general the question number 2 is to determine the work done. Okay, so work done, we need a general equation. Okay, so Q in plus work in plus summation of mass H1 plus V1 2 plus GZ equal to Q out plus work out plus summation of mass H2 plus V2 over 2 square plus dz. Okay, alright, so as we have all the figures, okay, alright, so basically the question is also given in the question is adiabatic, so which means that adiabatic, no work has been we take out. Also we don't have any work required as turbine produce output. Okay, so we have the mass also we can take out, same mass take out, so adiabatic out, so work out is H2 minus H1 plus V1 square minus V2 square 2000, sorry, this is H1 H2 plus G Z1 minus Z2 over 1000 Z1 minus Z2. Okay, alright, so from here we have the value we have calculated before, H1 minus H2, and this also we have kilojoule per kg. So we have calculated this value before. Okay, so substitute into the general equation, so we can have the answers. Okay, alright, so kilojoule per kg as m dot. Okay, how much? The last question is to calculate the mass flow rate. So as turbine produce 5 megawatt is in the question. Okay, so m dot, sorry, megawatt, okay, is kilojoule per second. What is megajoule per second? Megawatt, megajoule per second. Okay, so we have the workout kilojoule per kg, so we can take out megajoule. So we have m dot is 5 megajoule per second divided by, this is your value, something, kilojoule per kg. So here we take out, we left K. So adding by K, K is a answer, times 1000 K kg per second. That is your final answer. We have K, so K is 1000. Okay, right. Sample problem 3.17. Okay, sample problem 3.16. Air at 100 kilopascal kPa and 280 Kelvin temperature is compressed steadily to 600 kPa and 400 Kelvin. The mass flow rate of the air is 0.02 kg per second and heat loss of 16 kilojoule per kg occurs during the process. Assuming the change in kinetic and potential energy are negligible, determine the necessary power input to the compressor and take specific heat at room temperature. So 3.16. So in general, we have a compressor. So a compressor is similar turbine, but it require heat work input, work in. Turbine produce work out. So this is your state 1, this is your state 2, this is your output, this is your input. Okay, so given directly, P1, pressure 1, 100 kPa. Temperature 1 is 280 Kelvin. So P2 is 600 kPa. T2 is 400 Kelvin. Okay, the mass flow rate m dot given directly 0.02 kg per second, and heat loss Q out, heat loss. Okay, so we have a heat loss here, Q out is 16 kilojoule per kg. Okay, so this is the given directly. So general equation, Q in plus work in plus summation of mass. Okay, so we have H1 plus V1, val1 over 2 plus Gz is equal to Q out plus work out plus summation of mass H2 plus V2 square over 2 plus Gz. Okay, alright, so take out the unnecessary item. So basically here we have work in, Okay, so basically here it's not in has been mentioned because it's a compressor, work is required, and also the compressor doesn't need a heat supplied, so we take out. Okay, mass we can take out, mass cancel out together, and also the potential kinetic energy has been also negligible, and work out, the compressor is not producing output. Q out is there because we have a Q loss. So in general we have work in is equal to work in H1 plus H1 is equals to Q out plus H2. Rearrange, so work in is equal to Q out plus H2 minus H1. Okay, so this is all in kilojoule per kg. Okay, all right, so first state 1. So we are dealing with air. So P1 100 kPa, T1 200 kPa, 280. So PT is also given. So we need to determine what is your enthalpy 1. So H1 is CPT1. So it's directly kilojoule per kg. State 2. This is state 1 and state 2. So it's a similar. P2 given directly. T2 also given in the question. Okay, so H2 CP T2. So we got your answer, kilojoule per kg. Substitute into your general equation. So we have work in because work in is the question, necessary power input to the compressor. So we have Q out plus H2 minus H1. So directly, so Q out is 16 kilojoule per kg plus H2 minus H1. So substitute your value, kilojoule per kg. If the power, if you want the power, the question is necessary power output, so the power is in unit watt or kilojoule per second. So you need to, here you need to times kilojoule per kg times m dot, because you have kg per second. So you have a answers kilojoule per second or watt. Okay, thank you. Pump work very much like a compressor, except that they handle liquid instead of gases. Normally compressor will deal with gas and pump will deal with liquid. So general assumption, we have Q, heat, is well insulated, so that your heat is zero. We have no change in potential energy, and also no change in kinetic energy. So the volume is normally similar, and your internal energy is also similar. Thus your general equation is the pump required work in. So pump in is equal to mass times change in enthalpy. So knowing that your enthalpy is internal energy plus PV, pressure times volume, so we substitute this equation into your general equation. We have work pump in is U plus PV minus U plus P1, pressure 1, inlet V. So as the volume is constant, so the pressure is different. So we take out the pressure, so we have something like this. This is your general equation for work pump. And normally for state 1, normally we use saturated liquid unless specified in the question. If does not specify in the question, so we assume state point, initial point is saturated liquid. Sample problem 3.18. Sample problem 3.17. A pump is used to draw a fresh water at 1 bar and 30 degrees Celsius to a 10 bar. Determine the required work input and enthalpy of the water after the pump. Okay, so pump 3.17. So we have a pump. Okay, so this is your input, this is your output, state 1, so state 2. Okay, alright. So given directly, P1 is 1 bar, T1 30 degrees Celsius. Okay, and P2 10 bar. Okay, so here we are dealing with fresh water. Okay, so we can refer to steam table. Alright, okay, general equation. Okay, so we have Q in plus work in plus summation of mass H1 plus V1 2 plus Gz is equals to Q out plus work out plus summation of mass H2 plus V2 2 plus Gz. Okay, alright. So as the pump does not require heat, take out. Also does not leaking any heat losses, take out. And the pump required work in, so we take out work out. Pump does not produce any work. And mass also we take cancel out, as kinetic and potential energy as being negligible. So we have work in. Work in is H2 minus H1. Okay, alright. So here, as we are dealing with fresh water, okay, so for air, enthalpy is CPT. For water is H U plus PV. internal energy plus pressure times volume. Okay, alright. So we can substitute into the general equation. Okay, so H2 we have U plus P V P2 V minus U plus P1 V, as pump is a constant volume. Okay, so constant volume, pump is normally it's a constant volume, but the pressure is much more higher. Okay, so cancel out. So we take out U, we got V, the volume, P2 minus P1. Okay, alright. So state 1. Okay, we have 1 bar 30 degrees C. So at 1 bar 100 kPa. So what is your Tsat? Either higher or lower. Okay, so if lower than 30 degrees C, so it means that it's in the compressed liquid. So if compressed liquid, so we take T Sat 30 degrees C as our reference. So therefore, from here directly we can have HF what H1 is HF kilojoule per kg. Okay, we look into so also from H we have enthalpy. As the work is only required volume P2 minus P1. Okay, so V1 from state before this also VF, so directly given from the directly taken from you got meter cube per kg, we got V constant volume. So P2 and P1 is directly given in the question. So work substitute into the general equation, we got kilojoule per kg. Okay, alright. So as also we have work and work is H2 minus H1 from before this, the general equation H2 minus H1. Okay, so we arrange H2 work plus H1, so work here and H1 is from okay, so H2 kilojoule per kg. Okay, alright, thank you.